Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 17 titled Letter Combinations of a Phone Number. So I think this is actually a perfect medium problem, as the backtracking algorithm is somewhat difficult, and it does take a while getting used to. And I think this is a classic backtracking algorithm practice problem, just like how permutations was, and we actually did solve this problem on the channel just a few days back. So let's go ahead and dive straight into the problem statement, and that is that we're given a string containing digits from 2 to 9 inclusive. So basically that means that we're given a string from the range 2 to 9, including both of those numbers and the ends of the range, basically 2 and 9, and we simply need to return all possible letter combinations that the number could represent. And we can simply return this answer in any order. And so a mapping of the digits to the letters, just like on the old telephone buttons that some of you guys may actually still have, is basically given below. And we have to note that 1 doesn't actually map to any letters, and that's why we're given digits from 2 to 9 inclusive in our input rather than from 1 to 9. So, as you can see, this is the accurate mapping of the digits, and if any of you guys still have this keypad from any of your older phones, you guys can actually verify this and just check this for yourselves. But as you can see in examples 1, we have a digits input string of the integers 2 and 3. And we'd output the nested strings in a list of basically every single possible letter combination that can be formed from these two digits. And in this case, that would be A, D, A, E, A, F, B, D, B, E, B, F, and C, D, C, E, C, F. And note that every single combination is going to have the same length as the length of the digits input, right? So basically, the number of integers in our digit string input is basically going to match the length, or basically number of letters in each possible formed combination of our input. So if you want to actually zoom out just a bit, I think this is good enough, and we actually can analyze how this actually works, right? So we have the digits mapping of 2 and 3, and we see here that 2 maps to the letters A, B, and C, and 3 actually maps to the letters D, E, and F, right? And if we want to use one letter from each number mapping at a time, we can use the first A from 2 and the first D from 3 to actually form the first combination, right? And we can actually keep this A and move on to the next index here, the next element in our 3 mapping, and say AE. And we can keep doing that until we exhaust every single element within this 3 mapping with the first A in basically the 2 mapping, right? So we can have A to D, A to E, and A to F. Okay, we've exhausted every single element within our 3 mapping, and we can move on to B. We can say B to D, B to E, and B to F, and we can do this so on and so forth, C, D, C, E, C, F, and that's going to essentially form every single possible combination. If we apply that same logic to examples 2 and 3, we'd output A, B, and C for examples 3, and for example 2, since our digit string input is simply just adjacent quotation marks, or basically an empty string, we would output an empty list, because of course we can't actually form any possible combinations if we don't actually have any elements to actually analyze. So this is, like I said before, is a classic backtracking problem. And before I actually start with the backtracking approach of this problem, let's just go over the base case. And that base case is very simple, as we saw in examples 2. It would basically be if digits, right? If the input that we see is literally just equal to empty quotation marks or an empty string, we can simply return an empty list, right? We literally don't have anything to form, or any combination to form out of no elements or no digits in our input string of digits, and so we can simply return or output an empty array. Now, this is where we actually start with the programming, or not programming, sorry, but the backtracking approach, right? So like I did in my permutations problem, and literally every single backtracking technical coding interview question that I went on this channel, what we're going to do is we're going to have a final array, and we're going to have a so far array. With the so far array, basically building up the current iteration, or the current combination that we're forming of our input digits, and the final containing every single combination that we ultimately return after we've dynamically or recursively called the function to actually build it up with every single unique combination as we processed our input. So I'll say both of these are initialized to empty lists, because of course we actually haven't defined our backtracking function yet, or scanned through the array yet. So I will basically initialize that to be empty lists. And now I'll actually have my mapping, or basically my hash map mapping, for every single integer in my input digits string to its corresponding values or integers. So I'll say hash map. I'll literally just call this hash map, because that actually isn't a keyword in Python. I'll say, as noted by these curly brackets, for any of you C++ users, this is going to be the curly brackets that represent an array in the C++ programming language. And so I'll say that this empty string 2 is going to map to the letters of A, B, and C. And I literally just have to kind of do this manually, where 3 maps to 3 is going to map to D, E, F, right? And I'm basically just using this map that I'm provided here in the problem. So 3 is going to map to D, E, F. 4 is just going to map to G, H, I. 4 maps to G, H, I. 5 is going to map to J, K, L. And you guys can really skip this part if you just understand the gist of what we're doing so right now in this current hash map declaration, right? And I'm just going to take my time as I actually initialize and set these key value pairs in this hash map, because I don't want to actually make any mistakes in this video, just to make it as straightforward and concise as possible. So I'll say MNO, or sorry, my bad, I'll say 6 rather, should map to M and O. I'll say 7 is going to map to, okay, it looks like I went. 7 is going to map to P, Q, R, S. Oh wait, my bad. And 8 is going to map to T, U, V. And finally, our last inclusive integer in this problem statement is going to be 9. Rather the string of 9, because our input is also going to be a string rather than an integer. And that's, of course, going to map to W, X, Y, and Z. So that's just the basic hash map declaration, mapping every single integer that we could possibly have in our digit input string with its corresponding letters that we're going to ultimately use to form our possible combinations as we process through the input in our recursively backtracking function. So this is where I'm actually going to start our backtracking function. So I'll define backtrack, and let's talk about the parameter that I'm actually going to take in here, right? The parameters I'm going to take is actually just really one parameter, and that's basically the index that I'm currently looking at for one specific mapping or one specific integer within my digit string, and of course that's going to start at 0. So I'll literally just say index, and in this case I'll use I, and I'm literally just going to set that equal to 0, right? Because I'm of course going to start at the 0th index for whatever integer digit that I'm looking at in my input string. Looks like I forgot the colon to actually define this function, and now I'll actually have my base case like I always do in my backtracking functions. If the current index that I'm currently looking at, if that's actually equal to the length of the digits, as we talked about for each combination in our combination list, if that's actually equal to the length of the digits, great. I've found one more unique possible combination that can be formed from the digits in our input array, input string rather. And so I can basically add that to my final list of all these different combinations, and just to make it in form of string, I'll use this string.join method. And of course, I'll pass in the so far list. That basically the list of the current combination that I've built up that is actually a unique combination once it hits the length of the digits of my input string digits, right? And now, of course, once I've actually completed my base case, I want to just return and stop the execution of my function and move on to the next execution or the next call of the function to avoid any overcounting, right? So once I return, I'll actually loop through the indices, or basically the hash map at that specific index that I'm looking at for its corresponding respective mapping. So I'll say for, let's just say J in hash map, right? Basically hash map at digits at that ith indice. Okay, hash map at digits at I. What I'm going to do is I'm going to add that to my so far permutation, or not permutation, but rather combination. So far, using the .append keyword, I'm going to add J, right? And I'm basically going to keep doing that by recursively calling my backtracking function to continuously call, or basically continuously append these ith mapping integers within my input string digits to my so far combination, and I'm going to keep doing that until the length of that is actually, or the index that I'm looking at actually hits the length of my digits. And how do I actually update my index? Because if I just call backtrack and just pass in I, or basically the index that we're looking at right now, literally all I'm going to do is I'm literally just going to be stuck at the 0th index, and I'm not going to move on to any further indices to explore all the unique paths to actually build up any more larger length combinations. So I'm going to actually pass in I plus 1. So basically now I'm going to move on to the first indice, or basically the next element or next mapping of the integer value in my hash map to actually get the next possible value in my current combination. So I'll call backtrack at I+1. And of course, as I loop through hash maps out that digit at I in the C, high is of course going to be a default variable in Python in this function to set to equal to 0. And so I'm going to iterate over that and add that to my so far combination whilst I continuously recursively call my backtracking function with the next element, or with the next index here, basically I+1, until the index that I'm currently looking at of my input string digits actually hits the length of the digits so far, basically indicating that I found one more unique combination. But if I just do this, I'm not going to explore all the different paths, right? I'm literally just going to go through one linear path of just the corresponding JKL or MNO mappings of my input string digits, and I'm never going to go through every single unique path. So to kind of just undo and clean up the code that we just did, and basically I'm going to do so far.pop. And this is going to enable me to explore every single different possible combination from one specific iteration or mapping of my hash map and digits at I. And once I've done that, I've basically completed all the code for my backtracking function, and so I can simply call backtrack with, of course, if I really want to, a parameter of 0, although I is already set to a default value or parameter of 0. And once I call that backtracking function, I will have already dynamically appended the final array of all the unique strings that actually have formed different combinations of our input string digits, and so I can simply return final. And so unless I made any syntax errors or anything here, this should be completely fine. And okay, let's see what I did wrong here. Syntax error. Okay, if I equals the length of the digits. Let's actually run this to see the syntax error that I made. Okay, so that's going to be, okay, sorry. So this should be a double equal sign because we're actually comparing the digits to an empty string rather than setting it equal to the digit string, because we can actually put that in conditional. And so, okay, yeah. So I'm really bad at syntax, so pardon me for making these really bad errors. Well, let's see. Okay, so I just have an error in my hash map itself. Hash map is set equal to 2 with ABC, 3 with DEF, 4 with GHI, 5 with JKL, 6 with MNO. Okay, yeah, so this colon shouldn't actually be there, right? Because I'm not actually comparing that colon to anything, and it's essentially unnecessary. And as you can see, it's just about as efficient you can get, really beating nearly 100% of users runtime complexity-wise, and just about half the users memory complexity-wise. But in complete reality, these beats /% of users on Leetcode is basically random, and it is just almost randomly generated by the Leetcode compiler or generator or interpreter for Python, and so you really can't trust these numbers, but just know that this is just about as efficient you can get for this backtracking solution, and it's actually going to be big O of 2 to the power of n, right? It is a backtracking solution, runtime complexity-wise. Okay, so let's just kind of recap what this code kind of did. So basically, I just had my base case outside of my backtracking function. That's literally just the most basic base case that I can have for this problem. If digits is actually just equal to an empty string, I can simply output an empty list because I can't actually form any valid combinations if I don't actually have any elements to actually build a combination with. Then I initialize a final and so far lists to be basically the final list of containing all the different combinations of my processing of my input string digits, and the so far basically indicating the current combination that I've currently built up from the mapping of the digits that I use in my hash map mapping, right, which basically maps every single integer that I can possibly have in my input string digits with its corresponding letters, as we saw right here, right, in this map. After that, I actually defined my backtracking solution, right? So I defined my backtracking solution with a default parameter index I, and index I to be set equal to 0, because of course we start at the 0th indice of our mapping in our input digits string. And I have my base case first, like I do for any single backtracking function. If I actually equals the length of the digits, or basically the current index that we're comparing in our mapping, if that's actually equal to the length of the digits, we've exhausted every single possible value in our input string digits in our current combination, and we've basically got one extra or new unique valid combination that we found or dynamically appended, and so we can append that to our final array, which basically stores every single string of the combinations, right? And we use the dot join method to actually turn this array into a string, so we can more easily append it to our final array. And we can simply return to stop the execution of this function and move on to the next call of our backtracking function to avoid the overcounting of any combinations. After that, we actually loop through using the j iterator, and of course this iterator name can be whatever you'd like. And also for j, in hash map at digits at a specific indice, so basically the mapping of ABC or whatever indice that we're looking at, whatever number that we're looking at within our input string digits, we'll actually add that value or that letter that we're currently looking at to j, right? And we'll keep adding it to j until we actually exhaust or basically hit our index to be equal to the length of our digits once we've actually met our base case criteria, and we'll add that unique combination to our final array. And we'll simply .pop to explore every single unique path or unique combination of our input string digits. And once we've done that, we've basically ended our code, and we can actually just ended our backtracking function rather, and we can simply call the backtracking function with the default parameter index equal to 0 and simply return the final, which eventually and ultimately will contain every single combination of our input string digits with every single possible string of combinations, right? And you may be wondering, hey, once we actually append j, why can't we just append ABC directly, right? Why do we start with A and then append D and then E and then F with A being our starter? That makes no sense. And the recursive function that actually uses backtracking basically means that it tries one possibility at a time. It actually explores that path fully, kind of like a DFS or depth first search, and then it undoes the last choice before trying the next possibilities. And what this really ensures is that all combinations of letters are explored without actually combining them prematurely, right? So to kind of show what happens a bit more clearly, we'll have a first letter. In this case, let's just say example 1 in this case. The first letter, or the first loop, is basically going to pick the letter A, right? And it's going to add that string A, in this case right here, right? It's going to add that to our so far combination. And then we simply recursively call the function backtracking to explore the next digit. And at this point, the combination is incomplete. Basically, the length of it doesn't actually hit the length of the digits. And so the function doesn't actually move on to the second letter B or C until it actually fully explores the combination that starts with A, right? So after adding the first letter string A to our so far combination, the function moves on to handle the next digit in the digits input string. And for example, if digits is equal to 2, 3, after adding the string A, the function basically moves on to the next digit of 3 and tries every single letter associated with 3 in that specific mapping of our hash map. So basically both all the strings D, E, and F, and basically forms the complete combinations like AD, AE, and AF. And once we've basically exhausted or went through all of the elements for our 3 mapping within our 2 to A, we will simply move on to 2 to B, right? So basically, once all the combinations starting with A are actually explored, the function then removes A, or basically pops it from our so far combination, and then moves on to the second loop, right? Which is basically going to be B. And the process repeats, so B, D, B, E, and B, F, until it actually exhausts that as well, and moves on to C to explore every single unique combination, right? So, if you guys understood the solution and really learned something new, please consider liking this video and subscribing to my channel. This was a pretty lengthy problem and somewhat difficult to really digest at first, and so I tried my best to keeping the explanation as simple and concise as possible. And so once again, if you guys enjoyed this video and learned something new, please subscribe to my channel. It really does mean a lot and motivate me to keep going. And so without further ado, I will see you guys in the next video. Bye-bye.